Hi, this is Professor Cummings. I want to do a video on a technique for integration called U-substitution. Now, just to go back a little bit for review, remember the chain rule. The chain rule was a way of taking a derivative, starting from the outside to the inside function. So it was, if you had a function that was more or less stacked within itself, or two functions stacked within each other, you could use the chain rule to get a derivative. And the chain rule was as follows. So you have a function of h of x is equal to f with an internal function of g of x. Okay, so you've got this outside function we're just going to call f, and an internal function that's g of x. And the way you did this was to get the derivative of x, or derivative of h, you take the derivative of the outside function of f, leave the inside alone, and then take the derivative of the inside function. And the product of those two got you your derivative of h, or the derivative of the main function. Now to look at an example of this, let's look at this function here. So you've got y is equal to the quantity of 3x squared plus x raised to the fifth power. Now you just can't do the sum rule of derivatives, or the sum of the derivatives is equal to the derivatives of the sum, because you've got this exponent here. It makes it a little more complicated. So what we do is use the chain rule. So we got an outside function. You can think of this entire quantity as the outside function, and then what goes on between the parentheses is your inside function. So that'll be the equivalent of g, and the outside would be the equivalent of f. So the way we take that derivative using the chain rule, you look at the derivative of the outside, or f prime, which would just be 5 times the quantity of 3x squared plus x raised to the fourth power. So that's the derivative of the outside while leaving the inside alone. Then what we're going to call g, take the derivative of the inside function, so g prime. So it's just the sum rule for derivatives. The sum of the derivatives is equal to the derivative of the sum. So 6x squared plus 1. And take the product of those two terms, and you end up with y prime, which is just 5 times the quantity of 3x squared plus x raised to the fourth power times the quantity of 6x plus 1. And that's it. That's the chain rule. Just a quick review. So what if we wanted to take the antiderivative of this same function? All right, so if we want to take the antiderivative of that, how will we go about it? Well, look at this. You can't just FOIL it out too easily. You can, but it would be very complicated because of this exponent. So and then once you've done that, you can actually use the sum rule of taking integration. The sum of the integrals is equal to the integrals of the sum. But there's a simpler way of doing this, and that's what we call U-substitution. And the whole purpose of that is to simplify a complex function to take your antiderivative. Now, when you're looking at this, you're going to have to think of a couple of ways. How do you go about finding what you need to find in order to do this simplification? Well, first, you want to look for, one of the easiest to look for, a difference in the exponent of 1. That's just your first clue that you can work with. So in this case, you've got 3x squared plus x, and then you've got 6x, so you have a difference of 1, and you've got a 1 here as well. So that's one of the first clues. Another more in-depth clue kind of led from this first one is the simpler term should be a derivative of the more complex term. So in this case, you can do the sum of the derivatives and the derivative of the sum, and you can see that the derivative of 3x squared is 6x, and the derivative of x is 1. So this is a derivative of this. This is that 6x plus 1 is a derivative of the more complicated term. Now, one thing to keep in mind as you go through U-substitution and the chain rule is your basic rules of integration and derivatives, just the power rules, in other words. That's going to be a real big player, just to keep those in mind, not to mix anything up. So it might be a good idea if you're just getting warmed up to this to keep those on hand, just so you don't make any mistakes, just to keep yourself honest. So let's go ahead and work through this problem. So all I have is everything we had on the last slide to get the problem set up. We got our derivative rules, integration rule, basic integration power rule. We got our original problem, y is equal to the quantity of 3x squared plus x raised to the fifth power. We have our outside derivative and our inside derivative and the derivative of the whole function. So we got the chain rule laid out. Now remember our rules we're going to go through. So look for the difference of one to the exponent, and the simpler term should be a derivative of the more complex term. So that leaves us here taking this answer and wanting to get to a derivative of that term. See if this method is actually going to take us back to our original term. So we've looked at those rules, and we can see, and we already know that one is the derivative of the other, but let's lay it out, to do U-substitution. So we establish the more complicated term, and we call that U. There's my pen. So this is the more complicated term. We're going to call that U. All right. Now we're going to actually look at this. Since it's all been equated to U, we're going to take the derivative of U, which gets us 6x plus 1 dx. Now I want you to notice something here. So we have du is equal to 6x plus 1 dx. So you got a direct situation there, as well as u equal to 3x squared plus u. So what we can do from here is go ahead and say, okay, let's just substitute this right in. We have a clean substitution for both terms. So we end up with y is equal to the integral of 5 times u to the fourth du. 5's a constant, didn't really get affected by our substitution. So this is a lot easier to integrate than that original term. So if we take, knowing our rules of integration, the 5 comes outside the infinite sum sign. All right, and now we just take this term and we follow our rules of integration. Sorry about that, our rules of integration, where we take the integral of u, antiderivative of u to the fourth du, and you just add 1 to the exponent and then divide by the new exponent. So we have here that y is equal to 5, that original constant, 1/5, which is just the new exponent plus 1, and u raised to the fifth, and plus c. So our 5s are going to cancel. That's going to leave us with y equals to u to the fifth plus c. So that is our initial answer. Now we do our back substitution. Remember, u is equal to 3x squared plus x. So that was one thing we established earlier. U is equal to 3x squared plus x. So substitute that back in for u. And again, remember, you got to raise it to the fifth power. So you end up with y is equal to 3x squared plus u, the quantity raised to the fifth power, plus c, our constant of integration. And that gets us back to our original equation. So this did give us the antiderivative using U-substitution. And that's it. That's all you have to do. Just keep in mind you've got that constant of integration c, because right now we're looking at a family of solutions. But that is U-substitution. Thanks for watching. This is Professor Cummings.